Ah, greetings, mere mortals. Are you ready to learn the truth about the rainbow? Now, hold your horses, for here comes a revelation that will surely knock your stockings off. There are a lot of colors in nature, but only 72% of them are in the rainbow. You wonder why? You found the right video. It is I, Sir Isaac Newton, the esteemed 17th century luminary who formulated the laws of motion and gravity, and invented calculus just as a casual pastime. Now, I shall illuminate your intellects on the captivating subject of human color perception and the rainbow spectrum. Human color vision starts in the cone cells of the retina. A molecule called retinal absorbs light. Depending on the proteins it is bound to, retinal will absorb different wavelengths of light. Short wavelengths stimulate the S cones, medium wavelengths stimulate the M cones, and long wavelengths stimulate the L cones. Light with a wavelength of around 600 nanometers will be perceived as red. Wavelengths around 500 nanometers as green. Shorter wavelengths fall into the blue-violet range. Sweeping the wavelength across the entire visible range gives us the colors of a rainbow. The colors of the rainbow are the result of the separation of sunlight into its constituent wavelengths by refraction in water droplets in the atmosphere. These colors are the human response to light with single wavelengths. Combining two wavelengths will result in the additive mixture of the two colors. We can generate a color called aqua, or yellow, and a new color called fuchsia. Now, let's add a third wavelength to the mix. If we choose the right wavelengths, we can elicit the perception of white color. Changing the intensity of the three wavelengths can yield orange, or pink, and many other colors. This is how your telephone and computer screens work. However, we have seen that even a single wavelength can give orange, or aqua. It turns out that of all possible color hues, only about 72% can be generated by a single wavelength. These are called spectral colors. They are the colors of the rainbow. The reason for that are the spectral sensitivities of the three cone cells. You can see that due to the overlap of the L cones and the M cones. A single wavelength can stimulate both of them at varying ratio, giving us colors from red over orange and yellow to green. Similarly, the overlap of the M cones and the S cones gives us colors from green over cyan to blue and violet. The situation is different for the L cones and the S cones. There is a smaller overlap between the sensitivities of these two cone types. Also, a single wavelength in the overlap region will also stimulate the M cones, whose sensitivity surpasses that of the L cone. So the spectral colors are missing the hues that come from a mixture of the responses of the L and the S cones. These are purple colors, and they are not in the rainbow, unless two rainbows overlap. In case you wondered why the visible color spectrum is rather small, take a look at the spectrum of the sun that reaches the surface of Earth. Our eyes have evolved to distinguish the wavelengths that are most abundant in the sunlight. The sun's spectrum outside of Earth's atmosphere looks like this. Next time we will explain why it has this particular shape. So the apple, as it falls from the tree, does not only exhibit the effects of gravity, but it also reveals its distinct and visible colors to our eye. I invite you to ponder and share your thoughts on the following question. 1. How many wavelengths are required to produce a white color response? 2. What is your favorite color and why? Don't forget to show your support by liking and subscribing. Amidst the sea of misinformation, you can always rely on the great Sir Isaac Newton and the Leak Week to separate fact from fiction.